In this video, we'll be looking at integration of vector-valued functions. The following definition is a rational consequence of the definition of derivative of a vector-valued function. To do integration of vector-valued functions, you're going to be doing the antiderivative. So the antiderivative of the vector-valued function r of t dt is equal to the antiderivative of each of the components of that vector-valued function, whether it be in the plane or in space. And you can also evaluate definite integrals of vector-valued functions by integrating each of the components and evaluating the components with the bounds of integration. For this example, we're going to find the indefinite integral where we're integrating ti plus 3j dt. Whenever you have an indefinite integral or a definite integral, the integral should always start with the integral symbol and always end with a differential. And that, in this case, the differential is dt. That means you're going to be integrating with respect to t. To integrate ti plus 3j, we integrate each of the components. The antiderivative of ti would be t squared over 2I. And the antiderivative of 3j would be 3tj. And then we're adding a constant. Notice that the constant is bold. That means instead of adding a constant in front of the I component and a constant in front of the j component, we add a vector of constants. It's very important to distinguish between just a basic constant that you add in a traditional definite integral, and here we're adding a vector of constants. So we could have a constant for each of the components. What I'd like you to do now is try the following integrations of vector-valued functions on your own, pause the video, and then come back after you have worked these out to check your results. Let's integrate the vector-valued function 4t cubed I plus 6tj minus 4 square root of tk dt. You're integrating with respect to t. We're going to integrate each of the components. The antiderivative of 4t to the third power is equal to t to the fourth plus a constant. You can add a constant here, or you can add that vector of constants at the end, which is what I will be doing. So the antiderivative is going to be t to the fourth I plus the antiderivative of 6tj, that's going to be 3t squared, plus a constant. We'll add that to the vector of constants at the end. And then the antiderivative of minus 4 square root of t, that t, the square root of t is the same thing as t to the 1/2 power. So we're going to add 1 to that power when we integrate. So if we have t to the 1/2 added to get 2 to the 3/2. And you're going to multiply the minus 4 out in front with what you get when you divide by 3/2, or you multiply by the reciprocal 2/3. And then we're going to add, that's your k component, and then we're going to add that constant vector of constants. So this can be simplified to write it like this, or you can even write it using the component form using angle brackets, t to the fourth, 3t squared, negative 8 over 3 t to the 3/2 plus a constant vector. And that constant vector you can write as c1, c2, c3. There are a few ways that you can write that. Let's do the next one. Let's integrate the vector-valued function e to the ti plus cosine tj plus k dt. The antiderivative of e to the t is going to be e to the t plus your constant, so e to the ti plus the antiderivative of cosine t. Antiderivative of cosine t is sine t, that's your j, and then the antiderivative of the k vector the antiderivative of 1, it would be t, it's your k vector, plus a vector of constants. Okay, for the last example on this slide, we want to find the antiderivative of the vector valued function secant squared ti plus 1 over 1 plus t squared j dt. We're going to integrate each of the components. The antiderivative of secant squared t is tangent t, that's your I, plus the antiderivative of 1 over 1 plus t squared, that's your inverse tangent. So you can write it as arctan, or you can write it as tan negative 1 of t, that's your j component, plus your vector of constants, c. On this slide, we have a definite integral of a vector valued function. I want you to pause the video, try this one on your own, and then come back and check your solution. To evaluate this definite integral, we want to integrate each of the components of the vector valued function, and then we'll use the fundamental theorem of calculus to evaluate the bounds. So we want to integrate the antiderivative of a cosine t would be a sine t, and I can use the ijk notation or the angle bracket notation. Since this one started off with the angle bracket notation, I'll continue with that. So the antiderivative of a cosine t is a sine t, and the antiderivative of a sine t is negative a cosine t, and we're treating a as a constant. And the antiderivative of 1 is t. We're going to evaluate that at the bounds from 0 to pi over 2. When we plug in pi over 2, we get a times the sine of pi over 2, negative a cosine of pi over 2, and pi over 2. Subtract what you get when you evaluate the lower bound, so a sine of 0, negative a cosine 0, and 0. When we simplify this, we get the sine of pi over 2 is 1, so this vector simplifies to a. The cosine of pi over 2 is 0, so the second component is 0, and the third component is pi over 2. That's your upper bound evaluated and simplified. Your lower bound, when you plug in 0, the sine of 0 is 0. The cosine of 0 is 1, so we get a negative a. And then 0 is the last component of the lower bound. Now we're going to subtract the vectors. So we get the vector a minus 0 is a, 0 minus a negative a is a positive a, and pi over 2 minus 0 is pi over 2. So the result of evaluating a definite integral for this vector valued function gives us a vector. All right, try this one on your own. The integral of a definite integral from 0 to 3 of the magnitude. Those double bars indicate the magnitude of the vector with components t and t squared. Okay, to find this, if our vector is t comma t squared, we want to find the magnitude of that. And the way you find the magnitude of a vector is to square each of its components, add them together, and then take the square root. So it's going to be t squared plus t squared, quantity squared, and this simplifies to t squared plus t to the fourth. Now this can be simplified. In fact, you could factor out a t squared from both of those. If you factor out the t squared, you get 1 plus t squared. When you simplify this radical, it's the square root of t squared and the square root of 1 plus t squared. So this can be simplified to t times 1 plus t squared. So since we found the magnitude of that vector with components t squared, we can set up this definite integral as the integral from 0 to 3 of the magnitude of the vector with components t squared. is t times the square root of 1 plus t squared dt. Now we have a basic definite integral. We can use some integration techniques to evaluate this definite integral. To evaluate, you need to use u substitution, where u will equal 1 plus t squared. So du must equal 2t dt. We have the t and we have the dt. What we are missing is a 2. So I'm going to put a 2 and a 1/2 out in front and rewrite this integral using the u substitution. So this would end up being the u to the 1/2 power is the square root of u times the 2t dt is your du. Now when I convert the definite integral in terms of t to a definite integral in terms of u, I also want to adjust the bounds. To adjust the bounds, I'm going to look at my lower bounds. Lower bounds, the original lower bound was t equals 0. If I plug t equals 0 into what I came up with for my u substitution, my lower bound for the integral in terms of u ends up being 1. Put a 0 where the t is and simplify to get the lower bound 1. When you look at the upper bound, the original upper bound was t equals 3. We'll plug that into the u substitution equation for plug 3 in for t and simplify. 3 squared plus 1 is 10. So the new upper bound is 10. By doing this, adjusting the bounds of integration, you're not going to have to go back and substitute back in. Now we integrate each of the components, we integrate the definite integral u to the 1/2. We're going to add 1 to 1/2 to get 3/2 power. So we're going to have a 2/3 out in front with this 1/2 also out in front, evaluated from 1 to 10. When we simplify this, we can plug in a 10 first. We get 1/3 of 10 to the 3/2 power minus what we get when we plug in 1, which is 1/3 of 1 to the 3/2 power, which simplifies to 1. So that would be our exact answer. Now I'm going to show you how you can use a graphing calculator to approximate that definite integral. When you are using the graphing calculator to approximate a definite integral, you can actually go back to the original definite integral before any substitutions were made. I'm going to quit out of the graph, make sure you have a nice clear screen, and I'm going to be integrating the original definite integral, and I'll write it out again here. The original definite integral that we came up with before we did the substitution was the integral from 0 to 3 of t times the square root of 1 plus t squared dt. This is what I'm going to put in my calculator. So to do that, I press the math button on a TI-83 or 84 graphing calculator, and you want to scroll down until you see the command to integrate a function. And for this calculator, we want FNINT, that means function integrate. We're going to integrate the function, and we're going to put in the lower bound, which is 0. Use your arrows to get to the upper bound of 3. Move your arrow to get to the space provided for t, and then the square root of 1 plus t squared, and then move your arrow to get to the end differential t. Alright, when you do that, you get the approximation to the definite integral of 10.207. Approximately 10.2. Okay, now if you don't have an updated version of the graphing calculator, the way that you would enter the command on a graphing calculator that doesn't have the updated version, you would find the command to integrate the function. You would type in the function, do a comma, and then your variable that you're integrating with respect to, comma, your lower bound, comma, your upper bound. And that would give you the same result as if you did it using the updated operating system.